So today we'll discuss about the anisotropy of strain-gradient elasticity. Yesterday we heard that in this full setting, strain-gradient elasticity is defined by 300 coefficients, and in its isotropic setting it's only defined by 7 coefficients. The question is, what are inside these two extreme situations? And we will show that between no symmetry at all and complete symmetry, you got 48 possibilities defined by different number of independent coefficients, and each one associated to a special symmetry classes. So to begin, here it's To begin, what is the necessity to enrich classical elasticity? For our motivation, we want to substitute a heterogeneous material with an homogeneous equivalent one, and we want to have at the overall scale to preserve some aspect of the discrete behavior of the matter. Here is an example that will be discussed further on this afternoon by Giuseppe, in which we'll look at the wave propagating inside an hexagonal lattice. At low frequency, when the length of your scale is great with respect to the microstructure, the propagation of elastic wave is almost isotropic. And as soon as you increase or decrease the size of your length, for your wave, it will begin to interact with your unit cell, and the propagation, which was initially isotropic, now begin to see the anisotropy of your lattice, and now tends to be with hexagonal symmetry. If we want to determine an overall continuum that describes this behavior, we cannot use classical elasticity due to the fact that classical elasticity is unable to see hexagonal anisotropy. So, as an overall continuum, classical Cauchy elasticity is not interesting. Another point that may be discussed by Martin Poncelet tomorrow is an experiment that has been done in static, in which we test a beam with a coarse inner structure, and we look at the influence of the central symmetry into the pattern. If we have a coarse inner structure and we load it in tension, if the pattern is non-central symmetry, we have the appearance of a spurious bending displacement. This bending displacement cannot be described within the realm of classical elasticity due to the fact that classical elasticity makes no difference between central symmetric pattern and non-central symmetric pattern. So once again, if you want to define an overall continuum that preserves this aspect, classical elasticity is not the good continuum to choose. So instead, we will use the simplest enriched continuum that can model these two aspects previously discussed, which is strain-gradient elasticity, in which the degrees of freedom are kept the same as usual, so just the displacement field, but you will take into your formulation, energetic formulation, not just the strain, but also the gradient of the strain. And so you will obtain in your formulation a third order tensor is here, which is the strain gradient. As a dual, by duality, you will also obtain another measure of stress called the hyperstress. Here, the setting is the classical setting that is studied by people making the assumption that the material is central symmetric. If we quit this hypothesis, we obtain the full constitutive law, in which a new tensor, fifth order tensor, appear that will make the coupling between strain gradient inside the material and the Cauchy stress tensor. Usually this coupling tensor is not studied. So if I take a closer look at my constitutive law, I will have now three tensors for describing the elasticity of my continuum. The tensor C, which is the classical elasticity tensor endowed with the classical index symmetry, minor 1 and minor 1 and major 1. And I've got two new tensors, the M, which is fifth order tensor, that make the coupling between strain gradient and stress, and also a sixth order tensor for second order elasticity. Those tensors are defined by index symmetry, and the dimension of the associated vector space are respectively 21 as usual for classical elasticity, 108 for the coupling tensor, and 171 for the sixth order tensor. If we sum up this different number, we obtain the 300 coefficient indicated yesterday. So, since we are interested in anisotropy, we want to know how the tensors that describe this behavior will behave if I make my matter, my body, transform into with a rotation. So, how constitutive tensor behave under material rotation? The rule for transformation in such a case, it's the tensoral rule. That means that the action of the orthogonal group will act as many times as your tensor has many legs. So if I make the rotation, or here it's not strictly the rotation, you got rotation, it's the orthogonal group, and also mirror operation and inversion, it's the complete orthogonal group. If I act on fourth of the tensor, G will act 4 times on my tensor, and so on, 5 times on fifth of the tensor, and 6 times on sixth of the tensor. That is called tensor action, and it's related to the Rayleigh product that we saw yesterday. So as soon as I know how my tensors are transformed under an orthogonal transformation, I can define the notion of symmetry group, which is the set of transformation, I hope non-trivial, that let my behavior invariant. But in some way, for what we're interested in, symmetry group is not the right object, because when you speak about the symmetry of an object, you speak whether this object has the square symmetry or the triangle symmetry. You don't indicate to the person you speak with what are the specific axes of symmetry you consider to say that your object has the rectangular symmetry. When you said that, indeed, you speak not about the symmetry group, you speak about the symmetry class, making in your mind the idea that this symmetry and this one are simply the same once you make the first one to turn and compare to the first one. That's the notion of the symmetry class, which is related to the notion of anisotropic system your behavior can see. Here it's an example of two identical cubes having hence different group but belonging to the same class. So once you have this notion of symmetry class, you want to know for a given vector space that is used to pick up your constitutive tensor, in how many anisotropic system your vector space can be divided into. That is the question, indeed, we have to ask about strain-gradient elasticity, and we have to ask this question for each one of this vector space taken separately before putting them together and conclude for the complete constitutive law. Doing so, we need to know how many symmetry class, what type of symmetry class, for each symmetry class, how many independent coefficients do I need, and at the end, if you want to make explicit computation, you want to know the explicit shape of your matrix operator in each one of these anisotropic systems. This information can also help you to analyze the result of some experiment conducted on material having complex microstructure, and you want to know what are the true number of independent coefficients. This result can help you to decide this point. But before giving this answer, I must be more specific on what symmetric classes for tensor can be. Since we are interested into the action of the orthogonal group, that means rotation, mirror, and inversion, symmetric classes must be conjugate to an element of the classification of Auffray closed subgroup. So to give my answer to this question, I had to introduce to you the closed subgroup of the complete action group, which is Auffray. So the complete classification of Auffray subgroup is a bit complex, but there is a first level in which all your different subgroups will be subdivided in 3 elementary type of subgroup. In mathematics, they are called type 1, type 2, and type 3. What is important, it's what is contained in each one of this type of set of subgroup. Type 1 subgroup, if you take a group in this category and look at the generator of the group, your generator will only be rotation. We have no mirror operation nor inversion. Type 1 is just rotational symmetry. As a consequence, type 1 is the group that are chiral. The chirality is associated to type 1 subgroup. In type 2 subgroup, you keep your rotation, but add as an extra ingredient the fact you can use the inversion. So generator are rotation plus completed by the inversion. It's defined type 2 closed subgroup. Type 2 closed subgroup are the central symmetric subgroup of Auffray. And left side there are the type 3 subgroup. In type 3 subgroup, you don't have just rotation, you have also operation with -1 determinant, but in the generator you do not have the inversion. Okay, for physicists, it means that you don't have the inversion, but you will have symmetry plane, but not enough symmetry plane to have the inversion. 3 orthogonal symmetry plane implied inversion, and in type 3 you have symmetry plane, but not enough. So it's the type 3 are non-centro symmetric group, and also not chiral group, due to the fact that you possess plane of symmetry. It's always more easy with figure. So here is 2 figures that illustrate type 1. I indicate axes with a number are axis of rotation, and the number is the order of the rotation. So it's just a 4-order rotation. Here I also have my 4th order rotation and also orthogonal 2-order rotation. So these figures are chiral, and the chirality are indicated by the arrow on the figure. I can have this one turning this side, and also another one that will turn the other side. So it's type 1 subgroup, just rotational elements. For type 2 subgroup, I will also add with a dot the central, the inversion. And if here I just have a rotation and the central symmetry, and here I will have the rotation, also 2-order rotation in the orthogonal plane, and the central symmetry. As a consequence, it will also induce the existence of orthogonal plane of symmetry. But I have sufficiently plane of symmetry to be compatible with the existence of the central symmetry. For type 3 now, I got rotational invariance, I got plane of symmetry, but not enough plane to inherit the central inversion. So the classification will be made with respect to all this, this group. Precise definition can be given, but I will not enter this detail because it will take a long time to precisely introduce the notation. So now I can give the main answer to the former question. So if I get back to classical elasticity, the answer I know since the end of the it was in 1996 that the correct answer to the symmetry classification has been provided by Forte and Vianello, and they show that the vector space is divided into 8 different anisotropy classes, and the associate matrix representation were known for a long time in the mechanical community. For example, we can find this in some paper of Merabadi and Cohen, where they provide for each one of these systems the associate matrix representation. For all the tensor in the constitutive law, results are far more recent. We obtain with Marc Olive, former PhD student, the complete classification in 2013, showing that for the vector space of 6 order tensor endowed with the symmetry of strain-gradient elasticity, we have 17 different symmetry classes. And in this table we have the associate number of independent elements in each one of these systems. And we also construct with Qishang E and Hongli Kwang in a paper in 2013 the complete set of elementary matrices associated to each one operator in this collection. But what remained partially unknown was what are the results associated to the coupling tensor. So what is interesting is that the coupling tensor is an odd-order tensor, and the complexity of odd-order tensor is far greater than the complexity of even-order tensor. This is due to the fact that the action can see the inversion in the operation. Hence, for this fifth order tensor, I've got now 29 symmetry classes, when I got only 17 symmetry classes for the 6th order tensor. This jump in the number is due to the fact that fifth is odd, whether 6 is even. And we recently obtained, and the paper is, has been submitted quite recently, a specific matrix representation for each one of this system. So in paper we publish a list of if you need to construct M operator in this case, for example, I got the shape of the matrix you should implement in your code. So we obtained the result quite recently. I will skip this. I will discuss very quickly this part because it's a bit technical and maybe not very interesting to spend too much time. To obtain the matrix representation, the first things we did was to turn the tensorial law of strain-gradient elasticity into a matrix formulation by defining some equivalent basis. Here it's in R6 and here in R18. So the elasticity tensor turned out to be a matrix in a 6 by 6 symmetric matrix. The A tensor became now an 18 by 18 symmetric matrix, and the coupling tensor turned to be a matrix of dimension 6 by 18. With this rule and associate conversion rule, it becomes quite easy with formal computation code to determine the invariance restriction imposed by any elementary group. So we provide the result in this shape, having here the complex matrix for my operator M, which is divided in elementary matrix, and this elementary matrix might be turned on and off according to the different anisotropic system I study. But what is important is I study independently the fourth of the tensor, provide some result. I study the sixth of the tensor, obtain other result, and ultimately study the fifth of the tensor and obtain another result. So we got 8 symmetry in first case, 29 in the second, and 17 in the third one. Okay, but now I don't study just those tensor pick up independently. I study a law that is constituted of this tensor. So I have, at the end of the day, to put these elementary puzzle pieces together to obtain the complete classification. And a classification is to pick 3 elements and study the symmetry classes. The answer is we got a lot of combination that can emerge from the different elementary combination I can consider, and at the 8, this elementary classification conducts to 48 different anisotropic systems that describe all the inequivalent combinations that can be constructed from my elementary pieces. Among those 48 symmetry classes, 39 are planar, so in plane symmetry classes, while 9 are spatial. I mean tetrahedral, octahedral, icosahedral, and so on. So I got the complete classification here with the number of independent parameters for the in-plane and spatial classes. And in the same paper, we provide at the end of the paper the way you can combine the different results you can have in the literature to, in each case, put those pieces together in a way that is compatible with the material symmetry you study. If you are interested in material having this kind of material symmetry, the associate operator will be constituted of an elasticity tensor having this elementary symmetry, coupling tensor having this elementary symmetry, and sixth order tensor in this having this elementary symmetry. So I guess I take my time, so it's the end of my presentation. There is some reference, and I will be happy to answer to your question. Yeah?
Can you go back to the slide 22? Probably you said that I have skipped that. So I was expecting here M is 6 to 18. Why do we see 4 times 4?
Because in order to put my result in a way that is much more easy to read, I split this 6, 18 into elementary block that may or not be turned off by symmetry, and the decomposition is here. I got a block that is defined by 14 non-symmetric by elementary matrix with 15 independent parameter. This one with 5th independent parameter, and 5 also independent parameter. It's another
block matrices that
in
the end you have 6 to 8.
Yeah, it's a block matrices sub-decomposition of my operator that coincide with the 6, 18.
Sorry, but this is the block, the computation which is suitable for non-centro symmetric, or it is universal for every symmetry?
Here,
can we conceive something
This one is for no symmetry. So here it's the global matrix for the coupling in non-symmetric material, and this global shape will be particularized in each one of the specific subcases. It's the generic one.
Only the strain is symmetric. Only the strain is symmetric, that you have such that you have six times.
Yeah.
That's all.
My
Strain measure is symmetric.
Symmetric, and hence, as I take the strain symmetric, my strain gradient is symmetric with respect to the first index, so it's 18. That's,
Bertrand, Albrecht, go ahead.
Thank you. In the strain gradient theory, the symmetry transformation consists of the second order and the third order tensor. So what happened to the third order tensor here? What do we know about the role of that?
With respect to the presentation you made yesterday, you mean? I did not take this point into my formulation. I just make act on my tensor are just transformed in orthogonal way. As a consequence, as I turn my body in this orthogonal way.
Yeah, but the third order tensor opens many new possibilities.
But you mean the third order tensor as the strain gradient?
I think it's the one that acts on the strain gradient.
Ah no, I did not consider this case.
The symmetry transformation.
Yeah. Okay. I was not aware of that fact. I only consider it in a small displacement setting and not consider how third order tensor acts. It's independent?
Small or finite strains, or linear or non-linear.
Okay.
Should be there.
Okay, so I do not look at this point.
I would like to ask a very practical question. If we would like to apply this kind of theory to some material, let us imagine we have a polymer, for example,
Yeah.
which is crossed in some way, a very small portion of polymer. Now we have all this information from X-ray, we have Raman spectra, we have all this microscopic information. Is there a way to use this information to get some idea what these coefficients are like? Is there a connection between these two words?
You will have connection through an homogenization procedure.
I wonder. I'm not sure. I mean, does it need to be homogenized? I'm not sure. Has anybody thought about this? I mean, it's a wonderful theory. We have many coefficients. We have, on the other hand, we have a small piece of matter, some material, which shows some intrinsic structure. And we have this information about the intrinsic structure from the techniques which I described. So I was wondering, there should be some effort to bring these two.
Maybe, yeah.
Wolfgang, let's go to history of mechanics. How Saint-Venant identified the two Lamé coefficients, establishing two kind of deformations and making two kind of measurements, which became standard. So I think that it is a terrible, without using data-driven theory, data-driven, but using theory-driven, you can postulate that a material is governed by these constitutive equations. Then you start, then you are allowed to gather millions of data about deformation, and then you best fit the coefficients. This can be done, I guess.
How do we know this is the right theory for this material?
You need a vision. This is the conjecture.
Indeed, what has been done in some work.
The key square test can tell you if it is not working, you change the theory. No, it's not.
But in some cases, I know people who make calculation from atomistic level with some extended potential, and at the end of the day, they obtained an operator that was, it was in a cubic system, they obtained an operator that was strictly compatible with the shape we give in prior way. In some way, we don't explain what the coefficients are, but if we make a theory that is compatible with the microstructure symmetry, and you construct your operator, it should have this shape and not other shape. By these results, you can also detect in numerical procedure also some error, because the answer will not respect the symmetry you have at the as your entry. Symmetry is an entry of your problem in this way.
Okay, I'm sorry, I want to comment this again. If you remember, Navier tried to identify isotropic macroscopic theories with an atomistic theory, and we have the famous Navier mistake, because he believed that everything could be described with one parameter. And there was a debate lasting more than 20 years until Green postulated the existence of a deformation energy, found the symmetry properties of the invariance of deformation energy, said we need two parameters, and finally they could discover that Poisson ratio is not 3/4, but can be everything between -1 and 1/2. So in my opinion, it is very dangerous to try to get general results with homogenization if you don't know the target theory. So you must build a consistent target theory, and then you ask for the right microscopic models which, once homogenized, go there. This is the first comment. The second comment, while fluid mechanics has been completely well-founded with statistical mechanics, so you know exactly what has to be done, what is correct for getting fluid mechanics, you have all theorems of Boltzmann equations and so on, nobody knows how to get solids from statistical mechanics. So which are the interactions at micro level which are producing solids at macro level? So I think this is, in the present state of knowledge, very dangerous, because you risk to fall in Navier mistake. So this is very nice, I think, not because I'm friend of Nicolas.
Merci, Francesco.
You get a nice target theory. So you know that conservation of energy and symmetry gives you this amount of coefficient. Then you need to fight for finding the values in this situation or the other one. I think we are in terra incognita in this, up to now.
Sébastien,